So now we'll have Martin talking about the case against super-Eddington luminosities.
Higher, okay. Does that sound good? Okay, so I'm going to address the question of whether or not we're seeing super-Eddington luminosities, and I should emphasize there's a difference between an Eddington ratio for luminosities from accretion rate, because the two are not usually the same. So the problem, which I think by now we know well, is that the last decade or so we've been getting high black hole matter at high redshift, and how to get these is a challenge. One either needs massive seeds and or super-Eddington accretion there. So theorists have been suggesting that we've got luminosities which are several times the Eddington, and there's some papers there. And then the last about a year and a half or so, we've had claims by observers that we have objects with super-Eddington luminosities. So, for example, Su et al. In a paper in Nature last year claimed that there was 41 times the Eddington luminosity, and a couple of other cases I'm going to talk about as well. So a fundamental question with this is, are the high redshift AGNs fundamentally different from the more familiar low redshift AGNs? For example, in their structure and the X-ray emission has been suggested, for example, by Maddow and Hart. So that's the background there. Let me get a drink of water. So let me just give my takeaways first, in case I don't get to the end of the talk. Thermal AGNs. Thermal AGNs, those are the ones most of us care about the most. They're the ones with accretion disks. And I want to say that they are fairly well understood, and especially observationally. And so I want to talk about that. And then I want to analyze those claimed high Eddington luminosities, and I'm going to show that each one of them has some major problems. And then there's something I would have loved to have given you an entire talk on, is that many of the compact high Z objects with emission lines are not AGNs at all, but they're proto-globular clusters. That's a very, very interesting topic, but I wouldn't really have time to go into that. So how does one get an Eddington ratio? The Eddington ratio, I'm using lambda for it here, is the ratio of the bolometric luminosity to the Eddington luminosity. So for this, one needs to observationally get a bolometric luminosity and the mass of the black hole, because the Eddington luminosity depends on the mass of the black hole. Now, to get an L ball from observations in just a single spectral region, usually the optical, then one needs a bolometric correction. And hence, to do that, you need to know the spectral energy distribution and the reddening. So let's look at assume we've got the reddening done correctly. Let's look at a generic SED for a thermal AGN. Now, this plot here, this is a nice way of plotting things. Notice it's linear, nu F nu on the vertical axis, and it's log nu on the horizontal axis. And this has an interesting property, that an area under a curve here is energy. And so now we can see straight off that the energy output is dominated by what we call the big blue bump, or the BBB in the middle there. And this is the thermal emission. This is why we call them thermal AGNs. This is the thermal emission from the accretion disk. Now, that radiation is reprocessed in two main ways around the AGN. There's a lot of hot dust surrounding it, and so that re-radiates in the infrared over there. And then above the disk, actually one of the less understood parts about AGNs is a hot corona of relativistic electrons, and that inverse complement scatters up the photons from the big blue bump here into the X-ray region over there. And the object-to-object differences as a function of mass and Eddington luminosity here are surprisingly small in this SED. The main observational differences are actually due to differences in obscuration and reddening. The only place where things do change from object to object and do also vary in the same object is in this little box I've drawn here on the right here, with the edge, the vene tail here of the thermal emission, and in the complement scatter X-rays over there. I just want to comment about if you have any doubts about this. If you have run cloudy models, photoionization models of AGNs in the last year or so, then it's quite likely that you use essentially this continuum. Because this continuum I'm showing you here is the standard AGN continuum used in all the cloudy models you see. If you run cloud, it's called table AGN. An important point is if you don't have this strong big blue bump here, you don't get strong enough emission lines from the AGN. So this is well understood observation. Okay, so some comments on this. So from the optical to the near infrared, after you've corrected for reddening in the host galaxy starlight, that's pretty important, and they can be quite significant, and you remove the emission lines, then the continuum of all AGNs are consistent with a rising f nu to the plus 1/3 spectrum, which is the spectrum of, now how to put this in red, a lot of people don't know this, of an externally illuminated accretion disk. AGN accretion disks are not internally heated, they're externally heated. And that's required by the large amplitude of optical variability. The time scales for internal changes in accretion disks are way too long. They're like centuries, thousands of years, and we see them vary on weeks and things. Now, if we go to the far UV sort of X-rays, now there are two things that I'd like to remember here that I'm going to come back to. The lower the mass of the black hole, and this is obviously going to be relevant to high redshift, then the higher the energy of that vene cutoff we saw there, of the big blue bump. And that means we're going to get more soft X-rays. So lower mass black holes have more soft X-rays. And then for the other thing is for a given mass, if you have a high Eddington ratio, and again we're going to say this is going to be like what we're talking about in high redshift, then that again pushes the cutoff to higher energy and gives us more softer X-rays there. Okay, so remember that. Now, just above the accretion disk, and it's really quite thin, is the what we call the broadband region, or the BLR, and this co-orbits with the wave my hands around here. This co-orbits with the accretion disk, but it's turbulent as well. So the accretion disk, wave my hands here, and the broadband region is doing this. It's turbulent above it there. And a point about the broadband region is it is not outflowing. The accretion disk is opaque. We only see one side, and you see asymmetric blue-shifted, red-shifted line profile. Blue shift means going towards you. Red shift means going away from you. You only see one side of the accretion disk, so it's turbulent. It's not an outflow that we see in the broader region. Probably what you might hear sometimes. And then AGNs are very similar over the range of energy, which is photoionizing hydrogen. And since the broadband region occurring factor is also fairly constant, the strength of H alpha, say, or H beta, is a good proxy for the bolometric luminosity, and that's been over a long time. Okay, so to determine black hole masses, what we care about here, again, I want to repeat that the broadband region is gravitationally bound. That was shown a while back with velocity resolved reverberation mapping. So therefore, when you establish that, you can then, from the virial theorem, determine the mass of the black hole. Here's the standard equation here. F is a scale factor that depends on geometry of order unity. R is an effective radius. Delta V squared, delta V as the line with typically the fourth half maximum. And of course, G is big G. So you want to determine R, and So if you cross-correlate the line continuum and line, the continuum and the line flux light curves, then that gives you a lag, if you call it a lag in this business, and that is the size divided by the speed of light, and so you get a responsivity weighted radius there. So therefore, reverberation mapping straight away gave a mass and hence an Eddington ratio there. Now, this is all pretty observationally intensive. You've got to have lots of data, lots of telescope time, and so on. So what's much easier is something which was proposed by Ernst Debye back in 1977, and that is you can get masses from a single epoch spectrum. Again, the line width gives you the velocity, and you use the square root of the luminosity as a proxy for the radius of BLR. So one of the first things that we did with reverberation mapping was to verify that this works, and it does work very well. And since then, a considerable effort has gone into establishing this relationship between R and L here. What's particularly easy is instead of using the continuum luminosity, is to use the line luminosity, and you find equations for doing this, for example, in Green and Ho and Reyes and Voluntari there. Now, an important point here is sort of a super important point. You must be using broad line region lines for doing this. If you're using any other line, you're in deep trouble. And there are a few other requirements you have to satisfy as well. But the really important one, you must be using broad line region lines. And that's going to be a question where we get things at high rigid. Are we actually seeing broad line region lines? Okay, so if we do this for local AGNs, this is a sample of AGNs of ratio less than 4. Actually, ignore the bottom axis. That's about iron 2 emission, which is a different topic, not relevant here. Here's the Eddington ratio. What I want you to notice is these, in this observed sample, they go up to essentially stop at an Eddington ratio of 1 there. Now, there's observational uncertainties. There's also there's some systematics here, but you're not seeing points way up there. Now, let's turn to high reverberation optics. The first thing I want to talk about is LID 568. This is the one which Suator claimed an Eddington ratio of about 40, which is really high. That's good. Thank you. Just off the last diagram we saw. So here it is. I've covered up part of the diagram here, as you can probably tell. This is a figure from their paper there. And the green dots are from other people's UV selected AGNs. And pretty much as I showed you at low redshift, these they come up to and stop at, give or take a few observational errors, at an Eddington ratio of 1. Okay, now let's expose the bottom left of the diagram here. It's a bit more messy. So these are lots of determinations of black hole masses and luminosity, including some of the people in the room right now. I'm not too concerned about points with large error bars that would go up there. In fact, I'd be worried if there weren't a few down there. But now let's add into this one the Su et al. AGN, LID 568, and it is there. This is clearly an outlier. It's off by a lot. So if you read their main paper in Nature, this is what you see. Well, the thing I'm not happy about with Nature is Nature has supplementary material, which might be online, and you have to go and dig around to get it. So let's dig online. Let's go online and find the supplementary material, and let's see what a different version of this diagram. Oh, the luminosity has jumped down by about 1.5 orders of magnitude there. So what's going on here? So this purple star there. This is a standard determination, this is what I would do, standard determination of the bolometric luminosity from H alpha. But the authors in the main paper chose to only show, as you saw, let's go back to the slide, this one here, not the standard one here. The one they've chosen to show was an estimated L-bar from the X-rays, which is I would say one of the worst ways of getting L-ball here. So my only comment on this is that this would not have been my choice. Okay, let's move on to near spec 73488. This is the Myelina et al. They have two papers that year. This is the one in A&A. This is where they claim an Eddington ratio of 2.5. The most common BLR profile is a symmetric logarithmic profile. This is from Jack Baldwin's thesis here. However, many AGNs showed double peak profiles, and I proposed back in 1983 that these could be two separate black holes, each with a separate broadline region. And that's been a very popular, I'd say too popular explanation. But what gets overlooked is in 1999, I disproved this because if you've got two broadline regions, two black holes, then one's going to go like this and one's going to go like this. They're not going to vary together. They're going to vary independently. In fact, observations have always shown is that the two peaks go up and down together. And that means we actually got an accretion disk, and what you're seeing instead is that the two sides of an accretion disk, one side going towards you, one side going away from you there. Now, Myelina et al. have interpreted a normal logarithmic profile. So that's a reminder of what they look like. This is what it looks like in that object there. To my eyes, an AGN, that is a perfectly normal single-peaked profile there. But they've decided to interpret this into two components here. And of course, you can always take two functions or any number of functions and fit them to a line here. And when they do that, they get this Eddington ratio of 2.5. If you do the more normal thing that the AGN person would do, then you just take a single line width there, then you get a much lower Eddington ratio of about 0.5, which is quite normal for an AGN out there. Okay, so finally, let's go to GN 711. This one, a different Myelina et al. Paper in Nature, claims it has an Eddington ratio of 5.5. They got the massive black hole from magnesium-2, and they had this narrow line with it, and they get 1.4 solar masses and high Eddington ratio. There are several problems here, which I've discovered, at least the first one here. Problem number one is, if you look at the points in this paper here, there are no magnesium line widths down there. That's where the AGN occurs down there. And it's way lower than anything in the calibration. In fact, it's way lower than any known broadline region fourth half maximum there. And problem number two is that they then choose to say, well, hey, you get the same width if you go for use the nitrogen-4, but why use that one? We've got carbon-4 over here, much better line. As you see, that line, when you allow for the p-Cygni profile here, is way wider there. And so that gives about 10 to the 8 solar masses. So I'm out of time, so I should stop it. The neon 4 line is actually a narrow line. It's a narrow line region line. It has a low density. Neon 4 is similar again. So what we're seeing here, what we're trying to do is apples and oranges. We're trying to get a mass from the narrow line region, or a narrow line region. So this object does not have a super-Eddington agent. Okay, and as I thought I wouldn't have time to talk about why there's no AGN at all here. So let me just leave you with my summary here, won't we? Yeah. So I believe that AGNs, at least observation, are well understood, and actually many of these objects are not AGNs at all. But that, by the way, is because they don't see the lines we should see when you have a really hot accretion disk there. Okay, I'm sorry, I've gone slightly over.
Okay, let's thank Martin. Do you have any questions? Yes. And our next thing is going to be bullet point poster presentations. So if those people can come down here, I'll have that up on the screen just a second.
I agree with you about the Myelina results. I just wanted to point out a nice result by a former student of mine, Adam Thomas, in 2016, where he parameterizes the AGN spectrum and the big blue bump with a new model, which he characterizes the peak of the blue bump with a parameter called e-peak. And so we've actually been using that in our mappings models since 2016. So we've been including the blue bump in the models. So Pei-Shin, I'm going to, she's a student of mine here. If anybody's interested in AGN models that includes that, she's been working on that, and I'll be showing some results that include that tomorrow.
Go ahead.
I was wondering if you can expand on point number 3.
Point number this one.
Yes, the bottom
Yeah.
one.
Okay. There's a lot one can say about that. So if you look at globular clusters, they have high nitrogen, and globular clusters were formed when the universe was 1 billion years old, right about this redshift here. So from a globular person's point of view, and I've been talking with one of our local globular guys, Graham Smith, about this. He likes this. This is where we expect the globular clusters to form. They're compact objects. Now, the reason it's not an AGN is that there are two types of line you don't see. You don't see the very high ionization lines. I'm allowed to just go back to slide I skipped over. These are the energies you need to produce these sort of typical AGN lines. Stars don't normally get that far. If you have a low metallicity, you can get slightly further that direction over there and start seeing the nitrogen 4 and so on there. But you don't see these, especially like neon 5. You don't see it. And the other sort of paradoxic thing is you don't see strong magnesium 2 either, because AGNs give strong high ionization lines and strong low ionization lines. That, by the way, is the basis of the so-called BPT diagram there. So there's a lot of stuff not right here from an agent point of view. So is that enough? I think I've got to stop probably.
No, I guess I'll just follow up by saying, I mean, I have no personal preference of whether these things are black holes or not, but I think just claiming that the fact that there's elevated nitrogen doesn't make them globular clusters. I mean, globular clusters have other peculiar abundance patterns, but more generally, if you actually calculate how much nitrogen is in these objects, it's 2 orders of magnitude too low in order to actually make a globular cluster. We also see nitrogen-loud quasars. They're rare, but
yeah, well, the nitrogen quasar is the same thing. They're more common at higher redshift there. So the idea is the excess nitrogen is produced in massive stars, not as we formerly thought by secondary processing.
Okay, let's thank Martin one more time.